Pada pani dani pada baba gama dida sari pada pani dani pada baba gada pa pada pani dani pada baba gama dida sari ni sari madare ni sare sa ni sare.
Om Shri Sairam. Welcome to the last and the evening day 3 session for the Indo-US Conference 2. To take this session further, I request Ms. Rupashri to give the introduction for the speakers for the session. Over to Ms. Rupashri.
Thank you, sir. I welcome you all to the evening session of 3-day Indo-US Conference 2. As a part of an introduction, we have Dr. Roxana Lopez Cruz as a keynote speaker for this evening. Title of the talk is Media Coverage of Infectious Diseases. How does it affect their propagation? As a brief bio, Dr. Roxana Lopez Cruz did her PhD in mathematics at Arizona State University. Currently, she is full professor and researcher of the Faculty of Mathematical Sciences, UNMSM, and external advisor of national institutions on research projects in mathematics and its applications. In Latin America, she is recognized as an expert in the fields of mathematics, especially biomathematics, functional analysis, and delay differential equations, and the teacher training of young researchers for these areas. Her research interests deal with the biomathematics. She has developed scientific initiation courses and special topics in biomathematics. She ventured into areas of health consulting with the dissemination of mathematical models in epidemiology with exhibitions in offices related to that area in Peru. Over to you, Madam, Dr. Roxana Lopez.
Thank you. Thank you very much. Good night, good afternoon, and good morning for everybody who is in this special event. And thank you very much for the invitation. Well, I'm going to begin with this talk. It's very important for all of us to talk about infectious disease in moments or in times like this. And media coverage has an important role in this kind of problems. Then we try to do something about to make a link to introduce media coverage to the propagation of infectious disease. We are going to see the introduction, a brief introduction, the Zaire model, who is going to be the basic epidemiological model, then to check or to define in this case the negative feedback, and the new model coupling the negative feedback to the epidemiological model. Then we can check a brief check of the local and global stability of bifurcation of this model. This is the part, the mathematical part for us, and the other one is the answer for questions who people used to have for this kind of disease. And finally, a sensitivity analysis, not only by simulation, also by statistical methods like the sensitivity analysis that we use here. And finally, simulations. Okay. This work has the beginning not in COVID-19. COVID-19 comes after this, but we were thinking about what is going to be this link, the effect that is going to be of media coverage on infectious disease in any disease. But what we stay to think about negative feedback who is going to occur in this kind of problems. And we usually hear from the people of health, people in charge of health, that vaccination, for example, campaigns sometimes has a negative, not a negative, has myth, no? Myth to vaccinate people, or myth to make some non-pharmaceutical campaigns, and this is kind of thing that people begin to act in different ways. Then this is going to be an effect on the propagation of the infectious disease. Coverage media like this, coverage media in my country. I don't put here in my countries. It's in Spanish, but some of them has this kind of things. Then it's good. It's not good. Some coverage media is very, very important. Very important, because it's going to make the decision of people to have a good health or not a good health, or it's going to be the propagation disease in positive and not in negative that we need. Okay, then in this way we need to demystify a myth about COVID-19. This is one of the things that we begin to work in this case, because this was the news on all these 2 years. Then we have myths who goes to person, and this is a propagation in person simultaneously with the propagation of any infectious disease, in special in COVID-19. Then we were reading all these kind of things, and we were trying to identify how we are going to measure this kind of effect into the propagation of any infectious disease. Trying to do this. Then we have some lectures or some articles who were working about the global stability, still epidemic models, with the effect of the information, depending on information. Vaccination, almost all talk about vaccination. Then there is a lot of these kind of works, and we were thinking not only in a pharmaceutical measure or pharmaceutical strategy for all kind of pandemics. Then we were thinking that this information also is going to affect, but in non-pharmaceutical strategy. Which one? Isolation, quarantine, or any other that qualify like this, and not necessarily in vaccination. Then we were working on this, and then this is the base of this work. In this work, we propose and analyze an epidemic model in ordinary differential equation, including the index function as the effect in the propagation. This is going to be doing the non-pharmaceutical treatment parameter. For example, quarantine or isolation, as we call. And then our model has 5 subpopulations. So the first one is the classical, the non-isolated population as a susceptible. Isolated population with people who goes in the best way because government say you have to go, but then you know that this is not a good for a lot of people whose economic situation is going worst under the isolation population. Infected population, only this recovered population and death population. Why we put the death population? Because people here, for example, one of the questions when we were talking with people who is in charge of this kind of things in the health office, tell me that they need to know how it's going with the death population. Well, this is a model. Why? Because we couple the information index, who is going to be called N. Then this is the problem. classical in the first one. This is the new one. This is a non-pharmaceutical measure. In this case, it could be isolation or quarantine. Isolation is the idea here. And then we go from one to the other one, and taking in account this PM, that this PM is going to be the way which we are going to take isolation. And this is going to be influenced by the information. This information is not here. We can think that this is going to be the parameter who is going to be influenced. Why? Then this is not in this kind of model. Okay, if this is taken in account, we can put here any number, but it's better if we begin to think about to take another way to analyze this kind of model. Then we think in the negative feedback, and reviewing the all works, we have an idea to use this negative feedback. What is negative feedback in a biological system? Well, the end product of a process is to reduce the stimulus of the same process. Well, here in the negative feedback in an epidemiological model, because the first one was for any biological system, is going to change, automatically causes a corrective mechanisms of isolation, in this case, to start, which reverse the original change and bring the system back to normal. This one. Okay, if we have more people isolated, we are going to have less infected people. This is the opposite. And the other way of the negative feedback to make this cycle in this case is that if we have more infected people, we are going to have more isolated people. And this is going to be covered by the media, okay? Because the media has to tell us the truth in the right moment, okay? They don't have to take a lot of time. If this is going to happen, the time is going to be, or the delay in this time to get the information is going to make the best or the worst. Then this is a negative feedback, the system. And now in an epidemiological model. When we have to introduce the negative feedback variable, in our case is going to be given by this number. This number is going to take in account the time that you are going to take to propagate the information, the right information in this case, in the way that we need. More, in this case, more people infected that you are going to get to do the information, more people that is going to be isolated because it's going to take conscious of the disease. Then this is the way where the M represents the information index. GSI is the influence of the susceptible and infected. In this work, it's only infected people who is going to be the influence in the information dynamics. And PMS is the effect of information feedback that we explained some minutes ago on the disease isolation rate. Tau is the delay of the effect of the feedback on the information in the isolation policy, and are susceptible to avoid the contagion to disease. And finally, this is as the weight of this recruitment is chosen as the kernel of the delay. We can take some of them like fixed or special. We are going to take one for this. This is going to be the weak exponential delay kernel. And we working with this index, information index, is going to be transforming this one. Okay, then this is the system that we are going to study, and under this study we are going to make some assumptions, and these assumptions has to be real assumptions about the infected or the infectious disease. And they say if we don't have information, and the M is 0, we are going to have people who is going to go to the non-pharmaceutical strategy. Yes, this is going to be taken account. If the M is increasing, then PM is going to be increasing. and also that is going to have a positive velocity. For the G function, which is the influence of the infected population about information, we are going to take this in account only for infected. We talk about this, no? More infected people that you are going to go in the information, then more people who is going to isolate or take the non-pharmaceutical information. Then we get the R0 of the basic reproduction number, and some other one, that the Presmet ratio, who is going to R1, that is going to talk about mathematical results. And the mathematical results of this, the disease-free equilibrium always exists. The endemic equilibrium has this condition, no? R0 by R1 is going to needs to be greater than 1 to exist the endemic equilibrium. Then we have the disease-free equilibrium in this way, as the endemic equilibrium is this another one. All of this is taking into account, though you don't have the P of the G special node. They have some conditions, yes, but you can do this in this way. Well, then we are going to work with this one. R and D could be in terms of S, A, or Y, as you can. Then we have the reduced systems, and this is the reduced system that we are going to work. In this case, we can talk about the disease-free equilibrium that is locally stable with using the basic reproduction number and the ratio, the ratio that we defined before. Okay, and then we have some other result about the endemic equilibrium that is always local asymptotically stable, no, but under this other condition with these two numbers, special numbers that we are going to take in account. The sketch of the proof is very rapidly. We have to make a lot of things, algebraic things, to get this and to see what is going to occur with the characteristic equation, to see to check the locally stability of the endemic disease. And the endemic disease is going to be our special topic at the final of this one, because that one of the parameters, who is the inverse of the delay, taking in account the information, is going to be the bifurcation parameter. In this bifurcation parameter is going to go in terms of the Hopf bifurcation. This is the Hopf bifurcation, the result about this. Again, with this R0 and R1 and some other conditions that we have to take in account, trying to be the less conditions in such a way that this result was a good one. Then this is going to occur. We have to do some other things that we have to take into account with working with cubic and some other polynomials, working with some algebraic things. No? This is the transversality condition that is satisfied, then the Hopf bifurcation is going to go into this problem. And finally, this is going to be for the disease-free equilibrium, who is global asymptotically stable, the Hopf bifurcation that we have, and the sketch of the proof of this one, that this last one is going to be taken in account also for this model. Then we have all this is the mathematical results about this model, that in such a way that can give an answer to how it's going to affect the media coverage to the propagation of infectious disease. We can see some of these things with a sensibility analysis. This is the part of the statistical. Well, we are going to use a software in this case to make this, that is based in Latin hyperview sampling, Celsius ACE, and the partial rank correlation coefficient. We have to take enough numbers of data, and we check in the uniform, taking in account that we can see which one is going to be the parameter who is going to make the positive effect of the negative effect. The positive effect you can see here, and the negative effect you can see here. It's probably that we wait, because beta is the parameter of infection that is going to be affected by the parameter of the delay in this case. But the delay, the A that we can see before, is going to be the number who is going to make this kind of change. This is for the other one, the R1, the other parameter who is going to take in account to see how much is going to change. And this is for the reproduction number, R0. And this another one is for the R1, who is going to be mentioned in all the results that you can see before. Finally, we see some simulations, and we take into account that A, that is the inverse of the time to be isolated, or taking into account, to the inverse of the time who is coming the information, the right information to the people. Then in this way, we have these results for one, and the other one here is bigger than the other one, only to see that the change of the difference. Also for the desertion rate, that taking into account this, because people begins day by day taking into account that the economic situation is not good, and we have to take these kind of decisions. Then it's hard, but we have to take into account. And also the comparison of the evolution of fraction of epidemic populations and information index, all of they in the delay parameter A. The A is the parameter who is going to talk about what is happening also for Hof bifurcation. This is another one, the epidemic populations, and this is the populations in total for this simulation for all the subpopulation that we're taking into account in the SAIM model. Conclusions: we have presented a detailed discussion about the basic properties, existence, stability, and have studied the Hof bifurcation and endemic equilibrium. All this was good for us who are mathematical people, mathematics, working in mathematics, but it's better to take into account that we can answer people on health that has to take decision. But this is a hard work here in Peru. It's not so easy, because not everybody think that mathematical models can make change the mind about the useful who is the mathematical models. Well, we consider non-pharmaceutical control to reduce the spread of the disease and the influence of the information index into the susceptible subpopulation to take the decision to be isolated. So yes, this was our purpose. And it was very important to understand the dynamics of any epidemic disease transmission, especially COVID-19, and identifying the parameters of greater interest, which will help the policy makers in targeting prevention results for maximum effectiveness. We hope that in Peru the might change. Some of them use it, but they don't know how to change the model, to make more models, to solve more, to give more answers to all the questions that they have. We hope there are people, young people, who is working now, and we are very expecting that this change of mind is going better and better in my country. Our future research was also devise a delay in the isolation rate. The delay parameter will determine the chaotic nature of the disease propagation. This is the kind of thing that I am working now with the people here in Peru. Thank you very much for this opportunity to give this talk. Thank you.
Thank you, Professor Roxana, for the talk. I have a couple of questions. So that P of M you have taken, what is the exact function formula or the shape of the function, how it looks like, which deals actually with the media coverage.
Okay, this PM that you are talking about.
Yeah, because it
This
is
one.
the one
This one.
which
Okay.
decides the entire model.
This one, the PM.
Yeah, PM. P is a function
Okay.
of M, right?
Yes.
P depends on
Yes,
M.
this is the effect, no? PM is going to be the effect on
Yeah.
the
So how does
isolation. Right.
so it's
Yes.
a linear
This is
effect or a non-linear effect?
exactly. We have to take these considerations in this in the simulations. I use the linear, only the linear one. No, A by
Okay.
M, no more.
Okay.
Yes,
So
only this
because
one.
as
But what we could have more of them, we could have an unsaturation function. This is better, no?
exactly I was coming to.
Saturation. Yes, I recommend to use the saturation. All this kind
Yeah,
of
because I was
functions for
seeing,
this one. Yes,
especially when you said the saturation, I was trying to understand the different functional response, polling functional response. As you have
exactly.
taken linear, there can be polling type 3, 4
Yeah,
different functional responses, and we can go ahead.
exactly,
Yeah.
exactly.
So, are there any participant questions? So, yeah, yes, madam. So, we don't have any participant questions. So,
Okay.
on behalf of the organizing committee, Dr. Anuj and myself, we really thank you. I understand it's early morning for you, but still you have
No,
accepted
no, it's good.
our invitation, and as you have agreed to deliver the keynote address. So, Dr. Anuj Mubai has joined. I think he's traveling, so his signal may be a little weak. Over to Dr. Anuj Mubai.
Hi, Anuj.
Dr. Lopez Cruz, hello, how are you doing, Roxana? Good to see you.
Fine, thank you very much, and you. I hope to see you in Peru very soon.
Yeah, I will be there in like around 17th. Yeah,
Oh,
wonderful talk,
excellent.
actually, Roxana. Thank you for accepting our invitation.
No, it's an honor for me. Thank you. Thank you for
Pleasure
all
is
of
ours.
you, and congratulations. It was
Well,
I have my
thank you very
and the
much.
night and today and the day I was in your conference. Thank you very much.
Well, I want
Thank you.
to
Thank you.
let all the
Yeah.
audience know one very important thing of Dr. Lopez Cruz. She has been amazing mentor and a big organizer. She has been organizing mathematical conference for long time in Latin America, and there are um, investigators who are very well known in Latin America that have been participating in the conferences that she has been organizing. And it's not just one a year; she has been organizing every week, in fact.
Okay.
And plus, she is also part of some the country's national educational body, and so she is having a say on educational policy as well. So we are lucky to have her. That she could able to devote some time and share some her research focus with us. So we are very grateful. Thank you, Dr. Lopez, for being with us today.
Thank you, Doctor Anu. Bye. Bye,
Thank
host.
you. Thank you. Thank you,
Yes.
Thank
Professor
you.
Roxana.
Bye.
Bye bye.
So we have the next speaker, Dr. Aditi Ghosh. I request Miss Rupa to give introduction to her. Miss Rupa Shri.
Yes, sir. Thank
Excuse
you,
me,
sir.
I'm unable to share the screen. Like, it's not giving me the permission to, somehow, like, I'm unable to share my screen here.
Madam, can you email the slides to us? We will try to share
Yeah.
here, and it can be seen live on your StreamYard link.
Sure. Thank you.
Yeah. Meanwhile, Rupa, you can go ahead with the introduction, and then we will try to set the things up here.
Yes. Thank you, sir. The next keynote address will be delivered by Dr. Aditi Ghosh on building capacity for sustained collaboration and a study on optimal dynamic strategies of COVID 19 transmission in close contact facilities. As a part of her introduction, Dr. Aditi Ghosh is an assistant professor, Texas A&M University, Commerce. She did her PhD Mathematics, Texas A&M University, College Station. She has a certificate of achievement for STEM faculty launch participation from Worcester Polytechnic University. Her research interest lies in the area of mathematical and statistical modeling, computational mathematics with application to mathematical biology. Her research is driven by problems on public health issues, disease dynamics, epidemic spread, liver mechanism, social issues that requires mathematical formulation for its solution using modeling techniques. With this brief introduction, I hand over the session to Dr. Aditi Ghosh. Over to you, madam.
Thank you, Rupa. I'm waiting for my slides to be shown, and I'm unable to share it right now on the screen. So about myself, let me start. So as Rupa mentioned, I'm from Texas A&M Commerce. So this year, I just started from A&M in the mathematics department from this fall semester. And I would like to kind of talk more about what I do, how I do, and my research interest during the last couple of years. But I would really wait for my slides because it needs some visual demonstration. So give me a minute or moment to come up with those slides, and then I'll kind of pursue through.
Madam, your slides are up. We keep moving. I hope you can see the screen. Can you just confirm with us?
Yeah, I do.
So whenever you say the next, we will try to move the slides for you, madam.
Yeah. Thank you so much.
Welcome, madam.
So my talk today would be about the collaboration that I had been working on the last couple of years, and that had driven my research during those times. And one of my work with one of my students on optimal dynamic strategies of COVID-19 transmission in close contact facilities. In particular, we are talking about long-term care facilities here. So if I may go to the next slide, please. Yeah. So as she mentioned, I'm from A&M Commerce, and then I would like to talk something about my research and my collaboration that I had been doing since the last few years. So go ahead with the next one, please. Yeah, so I had been working with Dr. Mubai and my undergraduate students, especially during the last 2 years. So with Dr. Mubai, I have done a lot of projects, and especially with my undergraduate students, I would like to mention here Dominica. She had been working with me through 2019 on 2 projects, and I'm going to talk today about one of the projects that I have been working with her and which is due for a publication. And the other one here is Christine. She had been working with me since the last 2 years in UW Whitewater. She had worked with me on liver injury projects as well as beta transmission coefficient project, which I would be talking later in my slides. And then the last one is Claire. She is right now doing PhD in Northwestern University. She had worked with me in 2019 on a very interesting project on ischemic liver injury. So, by the way, Christine right now is in University of Minnesota pursuing her PhD, and Dominica is looking for a PhD program. She completed her internship in summer in CERN this year. And Dr. Susan Lenhart, she has guided us in the project. So thank you all of you for being with me here today. And this brings me to my next slide. So what I did in the last few years is my focus had been on liver injury. So in particular, I did 2 projects on liver injury. One was on acetaminophen overdose and its effect on alcohol consumption. So this was a very interesting project with the fact that all of us are aware of the paracetamol or the Tylenol that we take with our body aches or mild fevers or any sort of mild ailments. So this acetaminophen, which we hear and call as like Tylenol most commonly, has actually not a very good effect, I would say, on the liver if taken above the dose. So this causes liver damage, And apart from that, what role does alcohol play in that liver damage? So we studied two cases here, the chronic case of alcohol and the acute case of alcohol. And interestingly, as well as with clinical results, what we found out that there's a dual role of alcohol. So if alcohol is taken in a chronic quantity, or in a chronic way, you have a devastating effect on the liver on top of the injury caused by the overdose. But if acute doses, and depending on the timing of the dose, if alcohol is consumed along with the overdose, alcohol has an ameliorating effect on the liver. So the roles of chronic and acute alcohol were quite contrast in their application. So this was an interesting project where we developed a model to understand this dual nature of alcohol on the liver due to the overdose effect, and the timing. We were successfully able to kind of show through our model that it complies with the clinical results, and the damage depends on the timing of alcohol consumption. So this was one of the project with an undergraduate student from University of Idaho when I was working there. And she's the second author, Isaac. And we got to publish this, I think, in 2020. And the other project that I worked with was with Claire and an undergraduate student, Andrew. So this was on the liver injury due to ischemia or hypoxia, where we have oxygen deprivation in the liver. So what we found out while working in our mathematical modeling class is that no mathematical models exist for ischemia. So this made us quite drawn to the fact that why don't we start looking for building models for this particular liver injury and try to understand the effect of biomarkers for this liver injury. So what we did for this project is we developed the model along with the biomarkers, and then we validated this model or implemented this model on an existing literature, data from existing literature. And we could show that our model were making predictions for the biomarkers as was, or very near to the data that we have actually got from the literature. So this was, I think, a very crucial work during, I think, last year. And it helped me actually understand much more about hypoxia than I knew before while working with students. And I think now we have a full data from our clinical group where we can apply this model, even apply statistical models to understand the effect of ischemia on liver injury and prediction of the damage. So these two works were again with undergraduate students. And going to my next slide, I had another work last year on prion proliferation, and we were working on the treatments to understand the effect of treatment on prion proliferation. And this work was with Domenica. She led the project along with many other students. And what we found out in this particular project is that the combined treatment of interferons and chaperones, pharmacological chaperones, were much more effective in treating the prion proliferation than these treatments applied individually. So this was a very interesting project that we did. And the other project that I worked with my student Christine is, I think this got published in this summer itself, is estimating the transmission coefficient through data, incidence and prevalence data with application to Ebola and other health-related problems. So this was also an interesting work which I worked with Christine. And Christine currently is pursuing with me another liver injury project, which I think hopefully we can submit it by December or sometimes in the coming months. So these were some of the work that I did with undergraduate students, mind you. And going to my next slide, I also collaborated, started working on this project with Dr. Anuj Mubai on a chapter on reproduction numbers. So I would request all of you, like, this is accepted and it's going to get published, I think, in the couple of months, maybe sometimes by January, I would say. So if you get a chance, try to get a look into this, because the topic seems to be very common, reproduction number. We have all, I think, even for those of us who are even not related to the stream science, we now have understood reproduction number thanks to COVID, which kind of helped us understood its spread through this number. And we have often heard in news about this number getting higher or lower since the last 2 years. And we have worked on a chapter on this, which talks about reproductive numbers, not only from the context of epidemiology, but from other social relevant problems. So this is quite an interesting work, and I hope once it's published, we can kind of give more details on this. So going to my next slide, I also actively have collaborated with IBA, the Intercollegiate Biomathematics Alliance, which is housed at Illinois State University since the last 3 years, I would say. And this is the IBA is headed by Dr. O.J. Ackman. So what we do is we have a beer conference, national beer conference. Every year we come up with a beer conference, which is a symposium on biomathematics, ecology, education, and research. So this year also we have the virtual beer conference, owing to the fact that the pandemic still continues to ravage, and we thought it better to go virtually again this year. So it is around the next 2 weeks, November 12 to 14, 2021 this year. And we have tried to keep the registration fee as minimal as possible. So I hope to see many of you who are here today attending the beer conference. So when talking about beer conference, I must talk about an undergraduate research experience that is done by IBA again every summer. This one we had again virtually this summer. It's called CURE. And this year, running virtually, we had 5 groups of students who worked independently on 5 different projects with their mentors. And they have, we are coming up with this poster presentation for those projects in the beer conference. So talking about CURE, I have been working with CURE since 2019, and we focus on undergraduate students in this program, where the faculty mentors help the students come up with a research project, and in the summer, and we continue working with the students throughout, not only in the summer, but also in the fall, the coming fall after summer, so that students are able to kind of complete their project and make their presentation in beer conference. So this year, it's surprising that we had 5 groups, and many of them were international students. And thanks to the virtual platform, that many of them could work over in these interesting projects, and hopefully we'll come to see or know more about these projects in the beer conference poster presentation. So stay tuned on that, everyone. Like, if you're interested in a good research application talks and other panel discussions, you can look into the schedule of beer. So coming to my next slide. So I today want to kind of focus on a research project that I'm part with Dr. Mubai, Dominica, and Susan Lenhart, which talks about the study on optimal control and the transmission dynamics of COVID-19 in a long-term care facility. But before going to that, what kind of made us work on that project? First, it was the era, COVID times. During the month of March, I think we kind of understood in the United States the veracity of this virus, and it started spreading around the whole world around by that time itself. So few of the reasons that could be contributed to its spread is urbanization that happened in the last decades and the asymptotic nature of this disease. So going to my next slide. Yeah, so as I mentioned before, that this would be the topic of my talk today about the study on long-term care facility. And going beyond that, yeah, so this is the outline of what I'm going to talk is the construction of the model. What we have done in this model is capturing the super spreading event and the environmental transmission in a closed setting, and non-pharmaceutical interventions to control the spread of it. Yeah, next, can I go to the next one, please? Yeah. So I think during the time of March, this particular long-term facility in Kirkland, which is in King County, Washington, had made quite a headlines due to its outbreak. And when we collected the data for this outbreak, we kind of came to have the picture of the outbreak. On my next slide, please. So what we did find out that cases were indeed rising up for this particular long-term care facility. And when we tried to look into this data, we found that a modeling prospect, a mathematical model would be good to kind of understand the spread of this disease into the subpopulation of a long-term care facility, which includes visitors, healthcare personnel, the healthcare staff workers, and the residents, the senior citizens under care living in these facilities. On to my next slide, please. So we have seen these type of outbreaks not only in nursing homes, but any type of close contact places. For example, the Diamond Cruise that kind of made quite a headline due to its outbreak. So we tried working on this long-term care facility for our first project. So if I can go to my next slide to show what did we apply on the project, on the for the construction of the model. So this model had environmental transmission, which was, I think, a new thing that added to the SEIR model, and the non-pharmaceutical strategies to optimally control the spread. So as I mentioned before, so we had the subpopulation to be residents, healthcare staff workers, and the visitors. So the residents were there inside. The mobility was shown through the healthcare facility workers who could come in, who change their shift, or who could move in and out of the facilities. Even they could go to different facilities in the same long-term care. And then the visitors who would come from outside might introduce this virus if they are asymptomatic or symptomatic. So, and the other thing that we introduced is the optimum control to non-pharmaceutical interventions, which is either through mask or cleaning the environment, applying safety and cleaning hygiene inside the facility. So if I go to my next slide, please. So we applied SEIR model for both our residents and the healthcare workers. The visitors are captured with the variable EV. So we kind of assume that they were asymptomatic while coming to this resident facility, and they introduced this virus from outside inside the care facility. And the important part here in this model is the environmental transmission, which was captured by the concentration of the COVID virus in air. So that is denoted by C. And this is a framework for our model. So going to my next slides, this was the mathematical formulation here, along with the parameters, where an important factor is the tau, which is the viral shedding, which captured the viral shedding load for both the asymptomatic and the symptomatic visitors or the healthcare residents or the staff members. So going to my next slide, what we showed here is we considered 3 cases. The first case was when there was no super spreading event happening. The second one was when there was super spreading event with the residents. And the third one, the super spreading event with the healthcare staff. And these were all captured in our force of infection given by lambda R and lambda H. So going to my next slide, and we introduce our optimal control functions U1 and U2 for non-pharmaceutical interventions. And U1 stood for interventions wearing face mask, and U2 stood for cleaning or maintaining a safe, healthy, hygienic environment by preventing this transmission. So with this optimal control analysis, we constructed a functional whose goal was to minimize the exposed or the infected individuals and bringing down the cost for the non-pharmaceutical interventions. So which when we applied, next slide would be good. Yeah. So when we did this, what we found out is our reproductive number. We worked on a reproductive number on the 3 cases, and what we found out is that as usually or as expected or rightfully so, the non-super spreading event had a lower reproductive number, and the cases that contained the super spreading events had higher reproductive numbers. But interestingly, what we found out that even with the both super spreading events, we did see that case number 3 with healthcare residents, its reproductive number was slightly higher than with the super spreading event on the residents. And I can think of this because of the fact that, as I mentioned before, healthcare facility or the healthcare staff members had more mobility. They could move from one facility to the other. They were changing their shifts. So this contributed to a wider spread than I think would have been with the residents. So this is what our model kind of even predicted rightfully. So talking about the numerical results, about the control functions U1 and U2 when we plotted, we saw that U2 had the cleaning environment or the maintaining a safe or hygienic environment actually contributed to the prevention of transmission right from its inception. But for the intervention of wearing mask, it took some time to kind of control the spread. And rightfully so, because we know that wearing mask doesn't show the instant effect, but over time, it picks up with the control. So going to my next numerical results, with the infected populations, what we could show that, yes, the control, when we applied this control, we could bring down the peak of the outbreak. And this was evident in our resident population as well as with the healthcare staff. So in this particular diagram, the subscript R represents the residents without the control, and RU are representing the residents when control is applied. Similarly, for the healthcare workers, the H are the population of healthcare staff when control has not been applied, and HU stood when control was applied. And we can see from the results that the peaks of the outbreak were considerably down when we applied the control in non-pharmaceutical interventions. And this brings us to the summary. Yeah. Yes. So this brings us to the summary of what we found out, that we understood the transmission dynamics in these closed care facilities. for example, nursing homes, old age homes, where similar type of populations can be divided. But with cruises, it will be kind of little bit different because the population there was constant. So one of our future goal is to kind of understand the spreading dynamics of the vacation cruises through mathematical models. And if I Yeah, so this is what we mentioned. And the other thing that we want to do is we have not implemented real data into our model. So if we can apply the data from King County or the data from Diamond Cruise from public domain and apply it into our model to kind of see, I mean, the prediction nature, the predictability nature of our model, that would be great. And this brings me to the end of this particular project that we have worked since the last 1 year with my group. And thank you, all of you, for being here today. And before I finish, I have much time left, but I want to wish everybody a happy Diwali back in India and a happy Halloween here. We are looking to a colorful evening today, tonight, and tomorrow.
Thank you, Dr. Aditi Ghosh, for such a wonderful presentation. So I have quickly, do you have any audience question? Oh, okay. So I have a couple of questions, madam. So it's more being a mathematician, I'm tempted to ask, because we have also worked on a 9 to 10 compartment model, especially when we have taken a age structured model with respect to the different age groups, the younger lot, the adult and the older people. So the complexity when you're trying to do the stability analysis, for example, I see the model. So it's like when you try to understand the infected equilibrium or the disease free equilibrium, and you do the bifurcation analysis.
Yeah,
So how complex was it? Because some places we could not actually find it out. So only we numerically could demonstrate and do the optimal control studies for that setting. But of course, both are like a 9 compartment model. So I wanted to know, did you face what are the challenges you faced when you were trying to work on such a large compartment model?
actually, to be honest, for this particular, I agree with you completely that for any complicated models, it is really hard to kind of come up with the stability analysis analytically. So for this particular one, actually, we did not wanted to investigate the stability analysis. Our main focus was to understand the population dynamics for transmission of this COVID-19. And I think it for this project, I think it looked kind of easier, but where we stumbled mostly is not on the stability analysis, but we were constantly kind of facing stumbles on estimation, parameter estimation. That I think we focused much more to come up with the right kind of parameter to estimate or to predict the transmission dynamics for this model. So we did not kind of focus on the stability analysis for this one.
Okay. So Dr. Anuj, any comments from your
Something,
side?
Dr. Mumbai?
Yeah, yes. You have to unmute, sir. Dr. Anuj, you have to unmute. Or I think he's traveling, so his signal is a little bad.
Yeah.
Yeah,
No, he's
sorry.
getting it.
So one thing I want, great presentation, Dr. Ghosh. Thank you for accepting our invitation and being part of it. Um, one thing I wanted to share with all the audience is that with Dr. Aditi Ghosh, I'm actually writing few news articles in SIAM. It's very interesting articles, and maybe I will request Dr. Vamsi Dasu to share with all the participants. Those
Yes.
are good read because those are one thing we have realized in the COVID pandemic times is that how do you communicate your science or mathematical, which are for you it is very easy because you have been working on it for a long time, but how do you communicate with the audience of SIAM, for example, which is undergraduate students to someone who is working in algebra and have no idea about mathematical epidemiology, for example. So we have tried our level best, and it was an initiative by Dr. Aditi Ghosh, her research focus. I worked with her research group on liver injury. So I would encourage everyone to kind of go over those things. And also with Dr. Aditi Ghosh and Dr. Padmanabhan Sheshir and also Dr. O.J. Akman, we are organizing a beer conference, and it will be a good. I mean, Dr. Ghosh, would you like to say a few things on the beer
Yeah,
conference that?
yeah, I did mention about it in my presentation. So we are holding a beer conference this year virtually again from November 12th to 14th, and we are currently planning very interesting sessions of research talks as well as panel discussions and poster sessions. So I would request all of you to take a look into the beer conference schedule and see if it interests you. You can register and you can even submit your proposal for a talk or poster presentation too.
Thank you.
Just last thing, very quickly.
Yes, yes, sir.
So, you know, one thing we saw, Dr. Ghosh, in your talk is the incredibly beautifully you have worked with undergraduate students, and they are part of your research papers, which are pioneer paper in some of the very well-known journals in mathematical biology, for example, Journal of Theoretical Biology, PLOS One that you were showing. So it's incredible work. I mean, how do you, if you can quickly throw lights on, how do you encourage them, and how do they keep on maintaining the motivation in the projects?
Yeah, so one thing that I do is like I usually, when I teach mathematical modeling classes or ordinary differential classes, and in my mathematical modeling classes, I keep it an open, I do not have exams on that class. I just have projects, open projects. And I ask my students, whatever interest you come up with a project and we'll try to develop a model. And some of these papers has resulted through that actually, like they would come up with their own ideas, they would discuss it with me, and if I find that interesting enough and if they are interested enough, we would pursue those projects. And I think this had been kind of quite helpful in the sense because it was their project, and I asked them, it's your project, you own them, so you need to find the solution for it. And I think that motivated students, that I'm not giving something, but it is their work, they have to build it, it's their baby, they have to grow the baby. So I think that I think what I did in most of, and I think I personally would also like to do it in my near future with my students.
But madam, one, because I also do a similar kind of thing in mathematical modeling course, which I do. So a quick question is: suppose if they come with an area, which suppose we are a mathematician, suppose they come up a project in data science which interests them. So in such a situation, what do you do? If
So
suppose they
yeah,
come
I
up,
do support the students, and if I don't know something, I tell them I might not know this thing. It's your duty to kind of educate me on that. So for that purpose, every 2 weeks, I held a presentation in my class. So since there's no exam, no quiz, nothing, they would come up like every 2 weeks and present their work, and whatever improvement they have done, they will explain it to me. And that is how like I would get involved in the project. If I do not understand something, I would ask them like, why is this, why is that? And in order to answer me, they have to read more.
okay.
So that is they take the ownership of the project, and I think
Yes,
like
yes,
it has been a learning
Yeah,
process for me. If I don't understand something, that is fine, I'll make it sure that I understand through them, I learn through them. So
yes,
that is what I
and one
usually do.
one
I take ownership.
yeah.
one thing I want to quickly add. I know the time is running up. In the project that you were working with Dominica, since I was part of, I know that you actually involved Dr. Susan Leonard. She's an expert in optimal control, which students were in.
Yeah.
I think his signal is lost.
Mobile breaking, yeah. So what he was trying to say is like we were not able to understand.
So sorry.
Susan, yeah. Go ahead, Dr. Mobile.
So just saying that the project that I was involved with, Susan Leonard was is an expert. She's an expert in optimal control, and Dominica was interested in optimal control. So actually, you connected
These two,
with
yeah.
Susan Leonard, the right person for the project.
Yeah, I want to add something here. Particularly, Dr. Vamsi, answering your question, we had a very hard time on this project with estimation. So when we were doing optimal control, I think the weights, most of the books gives you an initial assumption, but how do you even come up with those initial assumptions? So those were the problems that we were facing. And I think we consulted Susan Lenhart, who had a book on optimal control. And I think
Yes.
she guided us a little bit, but I think that was a learning process for us, how to estimate those weights and those cost preliminaries for our numerical simulation. So
Yes.
that
Yes.
was something we were not very familiar, and we had to kind of struggle on that. Yes, I agree. And Dr. Len had guided us on that.
Okay. So as we are running short of time, we thank Dr. Aditi Ghosh for accepting our invitation on behalf of the organizers. So we move on to the next lecture. Over to Ms. Rupa for the introduction for the next speaker. Ms. Rupa, can you hear us?
Yes, sir.
Yeah,
Thank
go
you,
ahead.
sir. Uh, for the next speaker, we have Dr. Maya Mascheva, and her title of the talk is Parameter Identifiability and Optimal Control of a SARS-CoV-2 Model Early in the Pandemic. As a part of her brief bio, Maya Macheva is a professor of mathematics at University of Florida. She obtained her PhD at Purdue University in 1998. After that, she was a postdoc at IMA, University of Minnesota, Arizona State University, and an NSF Advanced Fellow at Cornell University in 2002 to 2003. Since 2003, she has been an assistant, associate, and full professor at the Department of Mathematics, University of Florida. Maya Macheva has published around 120 papers. She has published three books, namely Gender Structured Population Modeling in 2005 SIAM, An Introduction to Mathematical Epidemiology in 2015 Springer, and Age Structured Population Modeling in 2020 Springer. Her research has been supported by the National Science Foundation. In 2016 to 2018, Maya Macheva was a managing editor of Journal of Biological Systems. She has mentored 3 MS students, 13 PhD students, and 2 postdoctoral associates. With this, I hand over the session to Dr. Maya Macheva. Over to you, madam.
Thank you. Can you hear me?
Yes, madam. It's clear.
Okay. So, do you see my screen?
Yes. Can you make it full screen, madam? Yeah, a slideshow.
Just a second. Okay.
Perfect. Perfect.
Okay. Good morning and good evening to the appropriate parts of the world. I would like to speak today about parameter identifiability and optimal control of a SARS-CoV-2 model early in the pandemic. And what I understand here by early in the pandemic, I understand here the United States, the pandemic, the development of the pandemic in the United States. So I will start with a brief introduction about COVID-19. I'm sure we have all heard this many times during this conference. And I will introduce a model of COVID-19. And then I will focus on the parameter estimation and identifiability of the model. Then I will show you the model I will introduce originally is an outbreak model, so it can only capture one outbreak of the pandemic. However, in the United States, the pandemic already has 3 outbreak waves. So I will show you how we forecast multiple outbreak waves. And then I'll talk shortly on an optimal control problem that we formulated based on our model, and I will summarize the results. SARS-CoV-2 emerged in Wuhan, China, late in 2019. And as of October 25th, 2021, there have been nearly 250 million cases worldwide and 5 million deaths of COVID-19. COVID-19 was pronounced global pandemic by the World Health Organization on March 11, 2020. The pandemic has caused serious public health disruptions and economic loss. As of October 25th, 2021, the United States has had nearly 47 million cases and more than 750,000 deaths. The United States implemented lockdowns from March 2020 to May 2020, and it also implemented limitations to businesses and requiring mask wearing, which is still valid in some places. United States has had, as I said, 3 waves of the pandemic, and here 2 are pictured. The third one that is not pictured here, but I will show you later, is a more pronounced, meaning it reaches higher peaks. COVID-19 is transmitted primarily directly through droplet transmissions, and cases can be asymptomatic, mild, moderate, severe, and critical. Severe and critical cases can be hospitalized and result in death. So all these important features of COVID-19 will be captured in the model that I will present to you. So we have a whole conference on COVID-19, and pretty much everybody who works on infectious disease models and other math biology problems has made a model of COVID-19. So mathematical models have been widely implemented to study the spread and interventions aimed at mitigating the impact of COVID-19 pandemic. Model complexity has varied significantly from simple susceptible exposed infected recovered model, which is pictured in this flow chart here, involving few parameters, to more elaborate models with many more parameters that incorporate testing efforts, contact tracing, and social distancing protocols. Insights from the mathematical models that incorporate features of disease transmission can be used to improve our understanding of the spread of the disease and investigate optimal intervention strategies. So when we create differential equation models, we are often guided by potential questions that we may wish to address with the models. We often try to capture what we understand to be realistic features of the disease, or we are interested in linking the models to data, and this is the particular goal of this particular study. So the goals of this particular study is to study the identifiability of the mathematical model of COVID-19 relative to available data early in the pandemic, and to devise and investigate optimal control strategy for the control of COVID-19. So the data that we have used in this project are data from the United States. And we, as I mentioned, we are using data early in the pandemic. The data are start from March 3rd, 2020 and end on April 26, 2020. And we are using data both on cases, which are pictured here in this figure, and as well as deaths, which are not pictured here. So the model we have devised, as I said, is an outbreak model. It has 6 classes. The class of susceptible individuals. That one is decreasing by the force by the incidence of new cases, which is given by infectious of the exposed individuals, denoted by E, infectious by non-symptomatic individuals, denoted by IN, and infections by symptomatic individuals, denoted by IS. And the incidence is a standard incidence. In the denominator, we have the total population size N minus the hospitalized individuals denoted by IH. The new cases of COVID-19 moved to the exposed class, and from the exposed class at the rate K, they either become non-symptomatic or undetected. We assume that non-symptomatic individuals were not counted in the data, and or they move to the symptomatic class where they are detected and counted in the data. And from these two classes, the non-symptomatic and the symptomatic class, they recover, or from the symptomatic class, they can progress and become, develop severe symptoms of COVID-19 and become hospitalized, where they can also recover or die. The reproduction number of the model consists of 3 terms. Each term gives the secondary number of cases one individual of one of the 3 infectious classes is producing in the entirely susceptible population during their lifespan as an infectious individual. So the first term are the number of secondary infections produced by exposed individuals. The second term is the number of secondary infections produced by non-symptomatic individuals. And the third term is the number of secondary infections produced by symptomatic individuals. So we would like to estimate the parameters of the model using the data that I described. And we would like to study the question whether this is at all possible. So structural identifiability is a concept that determines whether a model is structured in such a way that its parameters can be estimated from available data. Structural identifiability is a theoretical result which considers perfect scenario, assuming the observations are given continuously for all time and are noise-free. A model is said to be structurally or uniquely identifiable if all the parameters P is the array of the parameters of the model, can be recovered from the observations Y. Y are the observations. In our case, the observations Y are the number of cases of COVID-19 and the number of deaths. So there are 2 sets of observations. Several methods for determining structural identifiability have been introduced and studied widely. Here we use the differential algebra approach, and we use the software called DAISY to compute the structural identifiability of our COVID-19 model. According to DAISY, the model, the way it is originally designed, is not structurally identifiable from observations of the daily incidences and deaths. So there are several ways to make a structurally unidentifiable model into a structurally identifiable model. One is to rescale some of the parameters, and the other is to fix some of the parameters if they are known from the literature. We are taking here the second approach. If the parameters alpha, gamma, and k and rho are fixed, then all other parameters are identifiable with exception of beta s. Beta s is estimated or is expressed in order to make the model identifiable. Even though beta s is not identifiable, we express beta s in terms of R0 and we pre-estimate R0. So with this structurally identifiable model, we fit it to the data as I explained from March to May 2020. And the first figure shows the fit of the incidences in the United States from March 3rd to April 26th. And the second curve, so the data are given by the red dots, and the blue curve is the solution of the model. And the second figure gives the fit of the model to the COVID-19 deaths in the United States from March 3rd to April 26th. To study, besides the structural identifiability, which is a theoretical concept, whether the model as designed is designed in a way that can reveal its parameters, or we can estimate the parameters. The second question is whether we can estimate the parameters in practice. So this kind of identifiability is called practical identifiability. And we perform Monte Carlo simulations in order to determine whether the parameters of our model are practically identifiable. Monte Carlo simulations are a sort of intense computational simulations which are based on taking the estimated parameters of the model from this fit here and calling that parameter set p hat. And then with this parameter set, we produce another 1,000 data sets for the cases and the deaths of COVID-19. And we fit our model to all these 1,000 data sets, estimating 1,000 parameter sets PJ sets of parameters, and then we compute what we call average relative errors, or RS. The average relative errors are computed by the formula on the bottom. So they are sums in this subscript J and I is actually the same subscript. So let's say J. For J from 1 to M is the difference between the J estimate of the parameter K and the parameter K true value over the parameter K true value, and adding all J estimates of the parameter K, which are, as I said, 1,000 of them, and dividing by their number, so by 1,000, multiplying by 100 to get a percentage. So the Monte Carlo simulations result in the following average relative errors for the parameters in the model. And here we have expressed beta E, which is the transmission rate of exposed individuals, as beta S times some coefficient QE, and beta N, which is the transmission rate of the non-symptomatic individuals, as beta S times QN. So as you can see from this table, beta S, the average relative errors are 78 when the noise is only 1% in the data. It is 223 when the noise is only 5% in the data. It's 294 when the noise is 10% in the data, and it's 426 when the noise is only 20% of the data. So as you see, beta S, first of all, the average relative error increase, which is normal as the noise in the data increases. But also the average relative errors are much higher than the noise in the data. So in this case, we call this parameter practically unidentifiable. Similar situation, we have similar situation with the parameter QE. The noise in the average relative error of the parameter QE is much higher than the noise in the data, and we call that parameter also unidentifiable. The remaining parameters, QN, nu, gamma S, and gamma H, which are the recovery rates and the death rate, have average relative errors which are much smaller than the noise in the data, so we call these parameters identifiable. So, as I said, the data in the United States data for cases and deaths has 3 outbreak waves, and we were wondering how we can fit this model to all 3 deaths. So we create a set of 3 models. So I here is the subscript of each model, and I varies from 1 to 3. So it takes values 1, 2, and 3. The coefficients AI, capital AI, take values 0 or 1. So A1 is 1 for the first wave and 0 for the remaining waves. A2 is 1 for the second wave and 0 for the remaining waves. And A3 is 1 for the third wave and 0 for the remaining waves. And we fit the model, this composite model, to all 3 waves. Here the data are what we are fitting to the data is this composite of incidences, and also the composite of the deaths. So you can see on this figure the black or dark gray bars are actually the data, and the blue curve is the fit of our model to this data. And you can see that in the first figure, these are the incidences, and in the second figure, these are the deaths. And you can see that the model pretty faithfully captures all 3 waves. And as I said, the third wave in the United States was most pronounced, meaning it has highest number of cases. Optimal control. So you know that many countries implemented a lot of measures to control the pandemic. The United States in particular initiated various community mitigation policies in March 2020. Some of the widely implemented strategies included the issuance of orders requiring persons to stay home, called also stay-at-home orders. Schools were closed and universities schools were not closed, they also transitioned online. University transitioned to online instructions. Stay-at-home orders started from California on March 19th and ultimately were issued in all 50 states. To model the social distancing introduced by the stay-at-home orders, we introduced control U1, which effectively reduces the transmission rates for the exposed individuals C and non-symptomatic individuals IN. To model the self-isolations, so in the United States specifically, individuals who are sick but not sick enough to go to the hospital were required to self-isolate at home. So to model the self-isolation at home, we introduced control U2. Both controls belong to the admissible set A and are bounded between 0 and 1. So the optimal control problem is similar to our original model, where we have introduced the reduction of transmission from exposed individuals given by the stay-at-home orders, which we model by 1 minus U1, and also the non-symptomatic infectious individuals who possibly do not know they are infected or infectious. So they also do not, so they follow the stay-at-home orders, so their transmission is reduced by 1 over U1. And the symptomatic infectious are assumed to be known, to know that they are infected, and they are obviously not in the hospital since we have a hospitalized class. So they're subject to the self-isolation control U2. So their transmission rate is multiplied by 1 minus U2. So the cost functional is integral from 0 to some finite time t of the sum of all infectious classes, E, IN, IS, and IH. And beta 1 U1 is the cost of the control U1, and beta 2 U2 is the cost of the control U2. So the integrand of the cost functional is denoted by L. And we use Pontryagin's maximum principle to introduce time-varying Lagrange multiplier vector lambda t, whose elements are called adjoint variables. And the adjoint problem is given by lambda t prime according to Pontryagin's minimum principle. And it's equal to minus h. H is the Hamiltonian, whose expression is given in formula 6. Dh dx, and lambda of capital T, this is the transversality condition, is equal to 0. So we solve the state variables and the joint variable system with the forward-backward sweep and a fourth-order Runge-Kutta method. So this is a methodology developed by Suzanne Lenhart, and it is explained in her book. The tuning parameters, or the weights B1 and B2, are taken to be 1. Since we bound the control functions between 0 and 1, the controls are mostly noticed by near 1. And looking at the impact of the control, so the first row of figures is the various classes. The first figure are the exposed individuals, the second are the symptomatic, the third are symptomatic, and the fourth one are the number of hospitalized. The first row are the controlled quantities, and the second row are the uncontrolled quantities. The last row are actually the controls. As you can see, the social distancing is expected to be at 1 for the majority of the time, and self-isolation is expected to be at 1 for the majority of the time. The impact of the control is that the peaks also still exist after the control. However, they are a lot lower. I don't know whether you can see that, but for instance, in the number of symptomatic individuals before the control, the maximum is around 5.5 times 10 to the 5th. And after the control, the maximum is about 3,000. So it's reduced a lot. So the peaks are reduced a lot. Interestingly, they are shifted to the left, so they occur earlier. And the most notable reduction in the peak is in the asymptomatic individuals. And in conclusion, we introduce a model of COVID-19 with exposed, non-symptomatic infectious, symptomatic infectious, and hospitalized. We fit the model to the early data from the United States. We use US cases and deaths data. We find that the original model is not structurally identifiable. After fixing some parameters, we find that the model becomes structurally identifiable. The parameters beta S and QE remain practically unidentifiable. We did not address that question. We formulate an optimal control version of the model. The controls are social distancing and self-isolation of symptomatic individuals. The optimal control suggests that both controls should be applied at maximum throughout the time considered, and this is given our weights, which were taken to be 1. And the optimal control leads to significant reduction in the infected cases. All peaks occur earlier and are a lot smaller, and the tending to 0 is faster. And I would like to thank my collaborators, Necip Tuncer, Archana Timsina, Miriam Nuno, and Gerard Chao.
Thank you, Professor Maya Macheva. I have one quick question. So, is this structure identifiability similar to, is there any relation with respect to structural stability? Because we work more on structural stability of a model, wherein you change the parameter a bit and see how stable is the model and how qualitatively the model changes. So actually it's an eye opener for me, because structural identifiability I'm listening to the first time. So is there any relation to your knowledge?
I have not worked with structural stability, but my guess is there is some relation, because particularly the practical identifiability tells you how much each parameter is clear, in what range it varies. So if it varies in a too large range, obviously we do not know its true value. So I would say that is not very stable.
Okay.
I would think.
Yeah. Yes. Actually, the structural stability, when we study, also we vary it in a very shorter range, and then see how good the same results will the same results hold, like earlier when we change the parameter in different setting. So yeah, as I understand, it's more or less like both lead to the same findings for the model.
Yeah, similar addresses similar problems. Yes.
Similar questions. So over to Dr. Anuj Mubai. Can you hear us? How is the connectivity? He's traveling. Dr. Anuj Mubai is traveling, so we may have little internet issues, the connectivity issues. Dr. Anuj Mubai, sir, can you hear us? Can you unmute the mic? Sir, can you hear us? So looks like I think we lost the connectivity. So on behalf of the organizers, so on behalf of Dr. Anuj Mubai also and myself, we will thank you, madam, for taking out your time and accepting our invitation as soon as it is sent, and accepting to deliver a keynote address. Thank you.
Thank you for inviting me. It was a pleasure delivering the address. Thank you.
Thank you, Professor. Thank you, Professor Maya Macheva.
Bye.
So thank you, madam. So for the next and the last but not the least, we have Professor Padmanabhan Seshayar. And before I call upon Ms. Rupa, so Professor Padmanabhan Seshayar was the co-organizer for the first Indo-US workshop along with Dr. Anuj Mubai. So I'm happy that he is here for a keynote address. So over to Ms. Rupa for introducing Dr. Padmanabhan Seshayar. Ms. Rupa.
Yes. Thank you, sir. Now, as sir said, the last and the final speaker for this whole conference is Dr. Padmanabhan Seshayar, and his title of the talk is Fostering Inclusive Modeling and Data Practices in a COVID-19 Era. As a brief introduction, Dr. Padmanabhan Seshayar is a tenured professor of mathematical sciences at George Mason University and serves as the director of STEM Accelerator Program in the College of Science, as well as the director of COMPLETE, which stands for Center for Outreach in Mathematical Professional Learning and Educational Technology at George Mason University in Fairfax, Virginia. His research interests are in the broad areas of computational mathematics, computational data science, scientific computing, computational biomechanics, design and system thinking, entrepreneurship, and STEM education. In 2019, he was selected as Figures That Matter and was awarded an honorary doctorate from Vrije Universiteit Brussels. This was given to committed scientists who transcend the boundaries of their own disciplines and to personalities that have been at the frontiers of societal change. With this, I hand over the session to Dr. Padmanabhan Seshayar. Over to you, sir. Thank you.
Thank you very much. Can you tell me if you can hear my voice clearly?
Yeah, yes, sir.
Okay, great.
Yes, perfect, sir. I hope it's
wonderful,
yes,
wonderful. Thank you very much.
You are used to, I think, most of the audience who are here, especially the participants from SSIHL, have listened to you for the National Science Day. So
that's great. Yeah, it's always great to be back.
So you're almost part of us listening to you again, sir.
Great. Thank you very much for the invitation. And, it is always interesting to be the last speaker at a conference, because most of the experts before me, they did a wonderful job at presenting all the important ideas to you and state-of-the-art work that is being done. So first, I'd like to congratulate you and Dr. Vamsi and Dr. Mubai for continuing the tradition. Sometimes conferences are started, but it's very important to continue the tradition. And I think, given the pandemic era we are all on, we were able to continue this on a virtual scale. So I think so that's one thing I wanted to start off with. Another thing about also coming as the last speaker is you have lots of people who have talked about uh, topics that are, when I mean inclusive, inclusive beyond just SIR, SEIR, SEIQR, and so many different things, but inclusive in the sense of including social behavior, like what Dr. Malai Banerjee talked about, including connection between economy and health, like what Dr. Sudeepa talked about, including connections between actuarial, tech, and data, like what Dr. Mudigunda talked about, including dynamics of droplets, as you travel, for example, like what Dr. Ratish Kumar talked about, and of course, impact on long-term care, like what Dr. Aditi Ghosh talked about, and recent talk by Dr. Marcheva talking about parameter estimation and optimal control. So, and so many of you, I mean, I can start naming everyone in this conference, giving so many different aspects of the talk. And what I wanted to do is, of course, all these aspects that I just said is outside of typical SCIR models, where you actually try to understand who is being impacted, what is being impacted, what policy is being impacted, and all that. So when I mean inclusive, as in going beyond just compartmental epidemiology models and seeing who's being impacted, what decisions are being impacted, and so on. So, and it could also impact curriculum on data science. And I remember, talking to the group here. So at any time, this is just my information about Twitter and LinkedIn. Feel free to get in touch with me anytime, and I'm happy to always connect and collaborate. So I'm not going to preach to the choir here, because most of you have been seeing lots of great talks on, when you have like you can do simulations, you can do data, you could have like what you're seeing is people with infected going and meeting people that are not infected, and then you could actually so one thing, what you're seeing here is, one thing is to depict things through models and SIR and SCIR and all that. One thing is to help everybody understand at a very low level, like look at the picture and say, oh, those brown dots are people with infection, and they're going and meeting people. So this type of language even a child can understand. So how, as mathematical biologists, can we actually take the language that we are delivering to experts? Can we do the same thing to teachers? Can we do the same thing to children? Can we do it at all levels? And so there's different ways to doing it. So I'll share some examples. So yes, we talk about spread. Pictures like this is very helpful to really say, like, one person gives it to two people, secondary infections, and before bogging down into R naught and things like that. Sometimes pictorial representations matter. Now, personally, my area is in computational mathematics and applying, to mathematical biology. It's been great to work with several people. But typically, it all starts with an SIR model, and then, typically you go from compartments to differential equations. Then you typically draw graphs, and then you try to find R naught. This is like the traditional, and then of course you can add on top of it optimal control and so on. And, as Dr. Banerjee referred to human behavior. So this is one of my students who was able to introduce a compartment. What you see here is, not only an SE, the I susceptible, and I symptomatic, and an I asymptomatic, a quarantine, a recovered, a hospitalized, a death compartment, along with lockdown and lift, like lifting the lockdown functions. And here's a model that has been published in the Computational Mathematical Biophysics, same journal that is having a special proceedings as well. And the student also worked on combining, normal behavior and not normal behavior. This was the second paper on mixing behaviors. So you can actually take these models and expand it into much more complicated. And you just saw several people also do this symptomatic infected, asymptomatic infected. Here's an example. But then if you look at this, novelty here is the confinement and how people actually change their behavior. And you saw some talks based on that. Now, I personally also have also work on physics-informed neural networks, where we try to actually understand error functions, and we derive the physics of what is happening from data. And just by knowing some data, can we actually identify the model out of it? So SIR, for example. And for that, we would use like neural networks. And you saw some talks by some of the folks who talked about how many layers, how many neurons, and things like that. And what type of equations are we trying to? What is the physics that we are trying to extract? And this is a published work from Letters in Biomathematics, and it's a very nice journal. And what you're seeing in this picture is the same standard London boarding school data with 14-day data. But then all you're given is, this data only knows that recovered. There were nobody, recovered at the beginning. And with just that, can you reproduce everything else? And of course, there's so many parameter estimation ways to doing it. But this here is just what is called as PINs, physics-informed neural networks. And we will be writing something about it in this proceedings, hopefully more. For example, this is something that we will write about. We just saw that most people use the susceptible meeting the infected. What if exposed people causing it? What if you have recovered people going back? And what if you have like these exposed people just sitting at home doing nothing and automatically recover? What if they die because of COVID in all these different stages? And what if they move from infected directly to recovered without a quarantine compartment? That's possible also. And just eat good food and drink hot tea. And some people have just it just comes and goes also. So the thing is, without treatments also, so how do you bring those, how do you keep expanding these models, right? So, and you can do this, and this is a recent work for my student, where you're just simply given some data points for just the infected and recovered, two things that you can easily get when you from a hospital, for example, and the infected again who come to the hospital. Suppose you have this, can you actually reproduce everything else? And this is just a simulated data where we started off with some simulation data, and we of course used pins to actually find let the algorithm find these parameters, and it actually estimates it using neural networks, and just an alternate technique to optimal control and all these other techniques. But it's a good parameter estimation technique. It's very reliable, one of the fastest techniques right now. It was published in Science as one of the fastest deep learning techniques. So this is by one of my former students who's a faculty right now. But we also validated against actual data, and it actually reproduces so well with every single behavior in terms of all the graphs and all that. But I also want to warn you that I always keep showing this. All models are wrong, but some are useful. Very famous George Box comment that we must respect. Why do I say that? Because sometimes we go too much into like, let's make the model so complicated that nobody understands, or let's put every single thing into the model. I also do that. But sometimes simplicity matters. So, of course, we try to do a model, and then we try to lower the curve and get the R naught smaller and all that. What we forget is that the health capacity is going up. So as we get the peak lower, but the health capacity, the number of beds is actually going, there is no beds in the hospital. So people need to be understanding that balance between number of beds. And so the model that I showed you with the student actually has calculates the number of beds in the hospitals as well. So, what for my first message is, let's all model for simplicity. Okay, what does that mean? There is this technique that I've presented to many students at your institution, but for the others that are listening in also, this is a very famous technique where I can ask something as simple as how many air-conditioned repairmen are in Delhi. And I can give you one simple information that Delhi has about 30 million as population. And I could make an assumption that every family has probably 4 people, mom, dad, and 2 children. So I could say that there are a number of families in Delhi is about 7.5 million. And then I can actually then say that not every house has a air condition. Maybe every fifth house has an air condition. So I can divide this by 5. And then I think about air conditioned repairman going to, Sarojini Nagar, and then they're going to Connaught Place and all those different places. Travel time is going to be taking a lot. So maybe they can do 2 jobs in the morning and 2 jobs in the afternoon. So that's 4 jobs a day. There's 7 days in a week. I don't work on Saturday, Sunday. So 5 days in a week, that's actually 20 jobs a week. There's 52 weeks in a year, but I don't work for 2 weeks in a year for vacation. So I only work for 50. Now you will have to understand how I'm making these estimations. I don't want to use 52, but I want to use 50. I don't want to use 7, but I want to use 5. Those are nice numbers. And I can do all that calculation in my head. So 4 jobs a day, which is 20 jobs a week, which is 1,000 jobs a year. So I can actually tell that there are around 1,500. And you can go and check how many repairmen are in Delhi. But what I just did is what is called as back of the envelope calculation. No SIR, no this thing, just to calculate something. This is called Fermi problems. Enrico Fermi, 1938 Nobel Prize winner, radiation physics, known for his contributions to World War II and Manhattan Project in the United States. But this is how we taught. He would go into the classroom and ask a very deep question, and the students have to figure out the concepts. Now we are missing this in the current age. We tend to tell students what we know, but we should be actually telling what the students want to know. Like what Dr. Aditi Ghosh was mentioning, we should ask them what they want to know. So this is where the educational paradigm shift is going to be happening. And which means, can we actually use such back of the envelope calculation without any SEIR or SIR or SEIQ or whatever it is, models, and tell how many beds are needed? And this is actually a paper that I wrote with Dr. Mubai, and you can actually, once you get these slides, you can see the links and all that stuff, and you can read how we did a very back of the envelope calculation without any modeling, simple ideas, and actually use Fermi ideas to actually calculate the number of beds. Modeling for context, it's very important. So we should be from modeling for simplicity to modeling for context. What do I mean by that? This is the famous map of the London epidemic when Dr. John Snow, the father of epidemiology, actually showed this map to students. Now I work with teachers and on using data science. We are creating a data science curriculum with this map, and we ask them to observe what are those black dots. Of course, if you look at those black dots, some of them are actually cholera-infested areas, many people that died of cholera. And if you look at that, there is also some little circular things, which is not obvious. So if you actually zoom in, you will see that this is all the people that died on the left side, with the red dots. But if you also see on the right side, there were actually pumps, like water pumps that were sitting right next to it. So it was just not a mathematical epidemiology problem. He looked at it as a problem from data science, where he put 2 maps together, and then he was able to figure out that pump that was at the Broad Street was infected. And that's how they figured it out. They didn't use any mathematical models. Very simple maps that's all they use to figure this out. And then once they figured out that pump was the cause, then they were able to actually backtrack and figure out and convince the policy people. So a second way to think about how to model, right? Modeling for simplicity to modeling for context. And of course, you can use this for social network analysis also. So, you could actually think about, for example, clusters that are created, and, you could think of who's the important person in the cluster. If you think about it, the person sitting right here in the center is really the person that is important, because if you break this person, all the clusters will be separate. This could be Bangalore, this could be another place, and this could be some other place, and this person is the communication between all 3. So it is important to understand this person. So while many of them think this guy is popular because he has 7 branches, but in reality, this is the person that is important. And so graph theory can help us understand, the importance of such a person. For example, if we know that these people are all infected, and you want to trace back where the infection started, I would not go to this person. I would go to this person. And so because what would have happened is it started here, and then it started to propagate across the graphs. And then so you can actually calculate what is called as, shortest paths. And you can actually go from, for example, A to B, there are 2 shortest paths I can go. I can go through John twice, so I can find a ratio. So this is called the betweenness score. And I can also calculate what is called, suppose A can go to B through another path, then the number of shortest paths just got increased. So, then the score changes. So you could calculate these things, these betweenness, and another score called the closeness. And based on that, you will see that this person in the center always wins. And so understanding this type of idea in a graph theoretic way is very, very important also. And this can help you understand about, these are all the links that you see, the nodes and the edges that you see here and all that stuff. Now, believe it or not, if you calculate these scores, John here in the center will have the best betweenness score, the best closeness score, and all that stuff. And in fact, this type of idea later on was used by FBI to track the mastermind for bombing the 9/11 attacks and all that. But why can't we use such ideas in epidemiology? And it turns out it is used in Bangalore, actually, Karnataka. You actually have people doing in Bangalore Medical College and Research Institute. They are actually using social network analysis to do these types of ideas and all that, and to track COVID tracing and modeling through a continuum. So we all do discrete approaches and also continuum approaches, but even then we write ordinary differential equations. But in reality, what if we can actually, and Dr. Ghoshal from BITS Pilani talked about this earlier, this is a work with him and one of our students, where we try to think of concentrations, like concentrations of these locations in time instead of populations. And then we talk about activations, a brand new theory for SIR models that we are proposing. Hopefully we'll be writing this for this journal this time. It's about connecting physics completely from continuum mechanics perspective and mathematical biology, probably one of the first times, and deep learning. This is probably the first time all three are coming together. So I'm very excited about this work. Hopefully we'll write more. Modeling for impact. This is my very favorite, because anything that we are doing must impact somebody else, not myself, not my growth, not my career, not my publications, not my it has to be for the user. So modeling for impact is very important. And if you're not already using it, please look at the blueprint by the United Nations called the United Nations Sustainable Development Goals, the 17 goals that are proposed by UNESCO and the United Nations, from everything from no poverty, zero hunger. You can see good health and well-being, which is where most of the health problems, health issues are to be addressed. These are 2030. You got time till 2030 to achieve these goals by the United Nations. They have 17 goals, 169 targets. There are targets within each of those goals. So if you're a student listening right now, I would strongly ask you to connect your work to something in this, because then it'll make it much more meaningful. For India specifically, it's all written in Hindi if you did not know. This is the Sustainable Development Goals for India. So it is actually very well, there's a whole group in India working on this. So feel free to get in touch if you want to know what these are and how these can be brought. And my job is now to connect mathematical biology and mathematical other topics to the Sustainable Development Goals. So it's, good health and well-being. As I said, each one has different targets. And you can look up a paper that I wrote on the World Medical and Health Policy, where I connect SDGs to domains, various domains and things like that. Also inclusive, while COVID was happening, there were lots of other things that were happening. For example, the opioid crisis was happening. Depression was happening. Domestic violence was happening. People completely ignored those things because you go into lockdown for example, the confinement model my student had done. We published this in 2 papers, social behavior, all that was great. Then we said, what's going on with this confinement? We talked to one of our co-authors, and she said, in Puerto Rico, there is a lot of domestic violence going on when lockdown happens. So we decided to look at the confinement compartment much more carefully. And so we created what happens inside the confinement compartment. We said there is people that are safe, people that are not safe because they are actually abused by people, and then they are victimized, and then they recover. So inside the confinement, there is a dynamics that is happening. So this is a very true story in terms of domestic violence that happens when you let people in lockdown. Alcoholism goes up and things like that. So we decided to study this, and we also decided to study this for multiple lockdowns effect, how the length of the lockdown impacts the idea of people staying inside the house. For example, does it increase the violence level? And this paper is already in review. And then we decided to even, what if the people inside have COVID, inside the house has COVID and giving each other COVID? So we broke down the victims as victims, exposed victims, infected victims. So, lots of people in developing countries stay in large families. So this is a very common thing. So this is again, a model that goes deeper into the confinement compartment and breaks it even further, and then connects it to the outside using these lockdown functions and lift functions and all that. And modeling travel, it's very important. So, this is a collaboration with my former student who's a faculty at Kingdom of Saudi Arabia. Hajj, think about Mecca, going to Mecca. The number of people that actually were visiting and number of people that were local, and how that interaction starts to impact these COVID models. So we are currently doing these studies with actual Saudi data and creating, R naughts, trying to understand the relationship between interactions between a visitor and a local, and different types of behavior. And you can see the models get much more complicated and all that. So, and finally, travel in terms of going back on the flight. Everybody's going to fly someday, and when you start to fly, there's going to be, like Dr. Ratish Kumar said, droplets going to come out of somebody's mouth that is sitting next to you who's not wearing a face mask. And that droplet concentration is going to be moved by the fluid from the air condition. And so now you need a model for the flow, which is Navier-Stokes. You need a model for the concentration, and then you need a model for the epidemiology. And this is my new project, which is basically funded by the National Science Foundation, where you have the fluid dynamics model coupled with the scalar transport for concentration, coupled with the epidemiology, coupled with airborne transmission, and then all of them coupled on a deep learning framework. So, and we are starting to get some preliminary results. For example, if you were to think of an aircraft and you have these vents from the top, and one of the people has COVID and they're starting to cough, what happens to this coupled simulation and things like that? And it takes a lot of work, and we are still trying to understand all these distributions and all that. So when I said inclusive, there's a lot more things beyond just the SIR and the standard machinery that people use. Typically a compartmental model, coming up with a stability analysis, coming up with an optimal control. This is very, this is where the world is living in the mathematical biology. And now we need to start translating that modeling for what? For publishing papers, for growing your career. I think it should be more for simplicity, more for context. It should be for helping others, and helping others to the point where it has an impact. Yes, everything that you all have presented have impact, but when you have that direct impact using a simple idea, then it's really powerful. And finally, I also noticed you also saw Dr. Ghosh present long-term care, and I'm fortunate to be working with both Dr. Ghosh and Dr. Mubai on understanding, when visitors come and visit long-term care facility, then there is nurses there is people in the long-term care facility, then the people in the community. So we are currently developing models, which hopefully we'll write up and also submit, which basically is also looking at the effects of lockdown on what is happening in the community, what is happening in the long-term care facility, what is happening between these two groups when they meet each other at a marketplace and things like that. So, just wanted to tell you, there is so many great things that you can all do, which you're already doing, in terms of taking this beyond the classroom and the research to actually, and you could say that, yes, I'm using real data. That's true. But then taking that idea from those that do descriptive SIR modeling to predictive, optimal control and neural networks and deep learning modeling, to prescriptive. So the three words: descriptive to predictive to prescriptive. And that prescriptive is where mathematicians can start to contribute. They're really looking for that. And sometimes we stop at the predictive and publish papers and stop there. I think it's time for us to move to the next level and work with public health experts, work with, there's so many people here, Dr. Surabhi Pandey, the Public Health Foundation of India. So without a true interdisciplinary collaboration, mathematicians cannot just do, you could publish and grow in mathematical biology or mathematics, but until and unless you work with a public health expert, listen to them and try to understand, not just talk equations to them, but really help them understand from a way that they will be able to take this back. And also policymakers, they don't care about the math. They care about this back of the envelope solution, quick solutions and all that. But math is important. So it's just a way how we actually communicate. So along with statistical thinking, mathematical foundations, computational thinking, communication is very important. As Dr. Mubai was saying, how you talk to the right people is very important. So with that, I think I just want to finish with this So it's great to work on different types of models. I've learned quite a bit interacting with several people, working on different models and translating it to other ideas. Like, for example, can I use infectious diseases to understand gang violence or opioid dynamics? And then ultimately, this is my current project that is pending a patent, where can I connect these mathematical models to help people that are, for example, drug addicts? And what can I do to help in terms of that? So here is a watch, for example, that is on people's hands, and that wearable is collecting machine data, and those data are constantly is churned using machine learning. And when the person wants to take drugs, they are thinking of even taking drugs, and there's a mathematical model that runs in the back. Immediately, the cloud will actually send an information to the cell phone, and the cell phone will have a friend or mother or somebody call the person and say, hey, let's go for coffee. So it's in the moment distraction. So how mathematical modeling can really be saving lives. And so I'm talking about going from innovative modeling to real innovation and entrepreneurship. So with that, I will stop, Dr. Vamsi, and I hope you were able to hear. So
Yes, sir. Perfect, sir. So thank you, sir, for showing all of us the wide variety of models which you are working, and also truly the interdisciplinary collaboration that you are having, and your add-ons to how to teach in a class. For instance, as you were telling, the Fermi problems. So let the concept, instead of the teacher teaching, actually the students indirectly understand the concept what we are trying to do. So thank you, sir. Thank you once again.
Thank you.
You are, I would say, you're no more an outsider. You and Dr. Anuj Mubey are part of our DMAX family. So thank you, sir, for being with us.
Thank you very much. Thank you for the invitation again, sir.
Yes, sir. Yes, sir. And hopefully next time when we
Can I
organize.
add? Can I add?
Yes,
of course, very much.
Well, Dr. Shashia, this was amazing that the way you summarized so many, and I think we did not do it intentionally, but it happened to be you as a last speaker. But it turns out to be an amazing thing that you summarized everyone's work, and we sometimes walk down to a very focused niche area and seeing the big picture. And not only that, you also gave a excellent wisdom of words about we have to, when we do the modeling, what is our goal is not to do the maths only. Of course, maths is important, as you said, but the overall goal is to help the society in whichever way we can. Unfortunately, before you, the previous speaker, Maya Mancheva, I knew her very well. I couldn't say a few things, but I'm really grateful actually that you take out time and actually talk about these things, and the work that I don't know if the participant know about it, but Dr. Shashia is also part of Virginia State STEM Advisory, which is a very reputable thing in US. So Dr. Shishir, could you please elaborate what is your goal and how you are helping these new generation of scientists through that program?
So yeah, briefly, I know we are at the end of time, but the governor of Virginia, which is like chief minister in a state. So I'm the STEM advisor to the governor of Virginia. So which means the curriculum that the entire state of Virginia will be running. So to give you an example, we are starting the first ever data science class, not a math class, not a computer science class, not a biology class. It is a data science high school class for 11th and 12th graders that is going to be introduced to thousands of students. So to do that, I have to assemble teams of people, educators, academicians, all coming together in how to get the future generation excited to actually work on what we are working on, but also giving them the feel for why mathematics is useful. So to get approval, you need to be a voice at the state level, talking to the governor and saying like, this is an important thing and so on. So it is going to, so it is already approved. So Virginia will be introducing the first ever high school data science sequence, which many more states will start to follow also, and hopefully more countries. So
Nice, sir. So, as there are no questions from the participants, let's all thank Professor Padmanabhan Seshayar. Thank you, sir, for joining us.
thank you.
Thank you, sir. Dr. Anuj, is your connection there? Dr. Anuj, can you hear us? Since I think since Dr. Anuj is traveling, any point of time, if he joins, we can add him to the live. So as soon as Dr. Anuj connection gets better, we will try to have him. So we are almost at the end of the conference. It was really enlightening and enriching one. So it's my pleasant duty now to give vote of thanks. Firstly, we thank the Sri Sathya Institute of Higher Learning Administration for giving us the necessary permissions and all the support needed for conducting this conference. Thanks are also due to the entire DMAX faculty and research scholars for being pillar of strength and supporting the organizers in successful execution of this conference. Thanks to all the keynote speakers for graciously accepting our invitation and delivering the lectures. Thanks to all the participants for being active audience throughout the conference. Special thanks to Mr. Raghuram, who is sitting next to me, Assistant Manager, MMLC, who was very instrumental for smooth execution of live streaming for this virtual conference. And also, I am grateful to Dr. Anuj Mubai, sir, without whose support, the conference would have not seen the light of the day. Lastly, we offer our prayers and gratitude to Bhagavan Sri Sathya Baba for his immense grace for this conference to happen smoothly and successfully. Dr. Anuj Mubai, I request your concluding remarks for this conference.
Well, I think you said it very well. Any successful event doesn't happen without a sacrifice of so many people. There are few of folks that you all have seen online live, but there are number of people that Dr. Vamsi was talking about, his students, his peers, and can you hear me, Dr. Vamsi?
Yes, sir. Yes, sir. We can hear you, sir. Yes, sir.
Yeah, so there is a number of people behind the scene that have contributed to this running of this program, and I hope the big goal of this conference was to give you outside this feature that we don't see it in on a regular basis in the conferences. Conferences are usually on a particular topic, and many of the focus as a students you may not be exposed to that area, and sometimes it gets a little boring also. So we try to bring the flavor by having people from different disciplines as well as industry folks. Now you can see what type of opportunities mathematicians are doing actually. For example, Calm Institute. I'm sure that many of you would like to work on a project, something that is on intersection of health and economics using mathematical models. So just these are the examples, and we hope to continue this thing in future with Dr. Vamsi. We have a tremendous success working together on many things, and we continue to do many of these things. And of course, without the effort of the Vice Chancellor, Sri Sathya Institute of Higher Learning, as well as the institute itself as a whole, it would have not been possible. So thank you very much from the bottom of my heart. And to all your participants, without you, it has not been possible as well. So thank you very much. So Dr. Vamsi.
Yes. I request the participants to stay back, continue to stay back in the Microsoft Teams for a very brief interactive session. So now we formally come to an end, and we close this Indo-US conference too with a prayer. Om Shanti Shanti Shanti. Jai Bolo Bhagwan Sathya Baba Ji ki Jai. Thank you all. Jai Sai Ram.